Hey everybody, Mr. Judson here. So we're done graphing. Well, we're not done graphing, but we've graphed all of our basic functions. What we want to look at today is something called function notation, or even really kind of cluing in to how maybe our A, B, C values affect not just a parabola, but how do they affect all the graphs? So I want you guys to take a look at these two questions. What do all of these functions have in common? So for number one, what do all of these have in common? Don't tell me they all have an x and they all have a 3 and we're all subtracting. That's not what I mean. Okay? If you were to graph these, what do they all have in common? And if you were to graph these four, what do they all have in common? I'm not looking for numbers. I mean, although there is like one number in the answer, but I'm looking for more of an explanation as to what happens. Okay, let's just think about it just for a second. All right, so I think a question like this, what they're really asking us is, how do all of these functions really compare to their parent function? How are they all different? Okay? And you know, we know what a basic parabola looks like. What this has done is it's shifted a basic parabola 3 units in the opposite direction. We know what a basic square root looks like. It's now been shifted 3 units in the opposite direction. I know what a greatest integer function looks like. I've just shifted it 3 units in the opposite direction. So every one of these is shifted 3 units to the right of its parent function. Okay? So each function is shifted 3 units to the right of the parent function. And what they're really trying to get us to realize is, as we put a C value in all these equations, right? It goes A, B, C, and then there's a D value out here. What the C value really does is it shifts your graph left or right. Right or left. Okay? And that's always the case. Now, it's not always exactly this number, because we always have to do the opposite of this divided by the B value to see how far it really gets shifted. Okay? But that's what all these have in common, is every one of these has been shifted 3 units to the right of its parent function. So what about these four? These are all D values. Each of these has been shifted where? We should say 4 units up, right? Because the D value shifts the graph up and down. So I'm going to say here, each function, I'm going to try and abbreviate this, each function, I'll just do F for function, is shifted 4 units up from the parent function. We're going to have some problems that are going to require a little bit of writing like this. So if you don't like that, I'm sorry, but we're going to have to do it. Yeah, so just get used to it. Try not to abbreviate too much. You know, don't make up your own shortcuts. And most importantly, go back and read what you wrote afterwards. It's amazing how many times people don't read what they wrote, and then you go back and read it and you go, what the heck? That doesn't even make sense. So yeah, you want to try and read through that as best you can. All right, so the thing that we're trying to think about today is if y equals x squared, we know that's the parent function, and y equals a times bx plus c squared plus a d value. Once I put numbers in here, what did that really do to this graph? Okay, what did it really do? I mean, here's what we know so far. We know that if I graph the parent function, it's just a basic parabola. Go over 2 units, you got to go up the square of that, which is 4. But when I come over here, I know that there's a vertex at negative c over b comma d. And then I'm going to somehow look at this thing to try and decide, am I doing twice as much as what's normal? Am I doing half as much? When this answer is larger than 1, what it means is that the parabola is stretching out in the y direction. It's getting bigger. Okay? The y values are getting bigger. You know, think about that. If you go 2 units over from the vertex, you got to square that, you go up 4. But if that's a 2, I got to go twice as far. I just increased the y values. When this is greater than 1, we're going to use the word stretch. We are stretching the graph twice as far as what's normal. If I do this and I get a 3, we're stretching the graph to 3 times as far as what's normal. If it's less than 1, then we're going to use the word shrink. Let's say we do this and we get 1/2. So we're doing half as much as what's normal. We're going to shrink the graph to half its normal size. So the stuff that we're doing today is really about describing how this graph is different from its parent function. What kind of transformations did we go through? You know, when we look at a graph of something, and let's just say that I've got this parabola that comes down and does this. Well, when I add d values here, what I'm really saying is add to whatever this produces. And it really means you're adding to the y values. So what it does is it takes this parabola and it shifts it up, if your d value is positive. If your d value is negative, well then it's going to shift it down a certain number of units. Now likewise, whatever your c value here is, we always do the opposite of that. So if c is a positive number, we're shifting this parabola in the negative direction. If c is a negative number, then we're shifting it in the positive direction. And usually what happens is we take our basic parabola and we shift it over a little bit and then up, and we've been more focused on where the vertex is rather than thinking about shifting left, right, up or down. We have to change our thinking a little bit, or maybe not change it, but add to our thinking. Okay? And so again, they're going to want us to describe, you know, what happened to the parent function to produce the graph of this equation. You know, what happens if a is negative? Well, then we take our parabola and we flip it across the x-axis. We're going to want to use that word, okay, flip. Sometimes people use the word reflect. That would be okay. But really one of those 2 words, okay, either flip or reflect. Don't say move it to the other side of the x-axis. All right, here we go. I just moved that to the other side of the x-axis. I didn't flip it or reflect it. Okay? Or what happens if b is negative? We're going to flip the graph across the y-axis or reflect it across the y-axis. Okay? When I shift this up or down, you know, again, there's certain words you can use. We really want to avoid the word move. Okay? You can shift. The word shift implies kind of like sliding it up and down, but you're not really changing the way it looks. The word slide is okay. Translate is a good word. Okay, so we're shifting or sliding or translating the graph. Same thing left and right. Shift, slide, or translate. Okay. the word move, we're going to say that's taboo. Don't use that word, okay? Things can move somewhere else, but they change their orientation. It changes the way it looks. Like if I move this parabola over here, oops, I lost part of it. I could also do that. There, I moved it. It involves rotations as well. And so that's why we want to avoid that word, is that it just has all kinds of meanings to it. Okay? Let me try and get that back where it was. There we go. All right, so let's do a sample question. By the way, just in case you're watching this and you're going, God, this just doesn't really seem like a big idea. Well, it kind of is. It shows up on the SAT test. It shows up on the Central Washington test. I've seen it on all kinds of different tests that people have to take. And so really this is a pretty important idea. Okay? So when I look at this, let me say one more thing. One of the things I always want to take care of first is, am I flipping it across the x-axis or across the y-axis? I always want to discuss that first. Because the moment you shift the graph somewhere else, it's no longer flipping across the x or the y-axis. It's now flipping across some other horizontal or vertical line. And as long as you get that right, then you're okay. But most people get it wrong. They stick to the x and the y-axis. So we want to do the flipping or reflecting part first. That's not happening in this one. Okay? So how is this different? Well, first of all, a times b squared is 2. So I want to stretch this graph to twice as much as its parent function. Okay, the parent function is this. F of x equals x squared, or y equals x squared. That's the parent function. How is this different? Well, I'm going to stretch the y values to twice the normal amount then I'm going to shift the graph opposite of this, negative c over b, so a -1. So I'm going to shift it left 1 unit and down 4 units. Then shift it left 1 unit and down 4 units. There it is. This is a writing assignment. Okay? How is this graph different than its parent function? Well, whatever this looks like, this looks the same, except we've stretched the y values to twice as much as what's normal. And then we've shifted it opposite directions, so left 1 unit, down 4 units. That's it, we're done. And what we've done is we have described the transformation. The word describe, scribe means to write, right? And transformation means, how is this function different from this one? What has happened? It has transformed. It's become a different picture, right? Well, we stretched the y values to twice as much, shifted it over left 1 unit and down 4 units. Okay? Let's try another one. All right, so my a value is negative. That means we're going to flip this graph across the x-axis. I want to do that first. So we're going to say flip. Now what is it that we're flipping? The parent function, whatever the parent function looks like. We don't have to say it's a greatest integer function. When I say flip the parent function, it means whatever the parent function is for that. So flip the parent function across the x-axis then I'm going to shift in the opposite direction, so -3, so I'm going to shift it left 3 units. 2.5 units. I'm not trying to graph it. I don't really care what it looks like. I just know that's what's going to happen. That set of steps is going to get flipped across the x-axis, shifted left 3 units, up 2.5 units. There we go. I want to say one thing about this, because this happens a lot. I'm a math teacher, okay? I'm not an English teacher. I'm not going to sit here and act like I have the best vocabulary and the best spelling skills in the world. Okay, I don't. But I know this. If you say flip it across the x-axis, you don't ever start a paragraph with the word it. You know, what is it referring to? There's a subject of a sentence, right? So we have to say, what is it you're flipping? The parent function. We should always have the parent function written here. Once you've established that you're talking about the parent function, then if somewhere else you say then shift it, that it is referring to the parent function, right? So it's okay to use the word it after you've established what it is that's getting flipped. I mean, if the only thing I did, let's say that negative sign wasn't there, and I'm going to shift this thing 3 units to the left and 2.5 units up, then I couldn't start with this, right? I'd have to say shift the parent function left 3 units, or 3 units to the left, I don't care how we word that, and then shift it up 2.5 units. Be real careful with that word it. All right? Make sure we've established what it is first, and then move forward. All right. Let's try one more. Oh, baby. How is this function different than its parent function? Now, some of you are going to look at this and you're going to go, I don't even know what the function is. I don't even know what he's talking about. And we don't have to know, right? Here's the thing. If I say f of x equals the square root of x, okay, or x squared, or 1 over x, you know, whatever, doesn't matter. When you do f of x minus 5, it means take this and plug it in there. So now, this thing is the square root of x minus 5. Okay? Now add 7 to it. We're not plugging it in anywhere, we're just adding 7. And now, take the opposite of whatever you just plugged that into. Okay, there we go. Flip it across the x-axis, shift it to the right 5 units, then shift it up 7 units. Here's why I don't care what the function is. Let's say I go back here, and now I'm going to say that I've got x cubed. How does this look different? Well, I'm going to take the square root out. I'm going to put cubic in there. I put an x minus 5 in place of the x, so I got that cubed. Took the opposite of it, and then added 7 to the whole thing. So now how is this different than this parent function? Well, I still flipped it across the x-axis. I still shifted it 5 units to the right, and I still shifted it 7 units up. The exact same thing I just said when that was a square root function. You want to change it to something else? Okay, let's call this 1 over x. All right, now what does this look like? Take x minus 5 and put it where the x is. Take the opposite of that, and now add 7 to it. How is this function different from its parent function? Well, it's been flipped across the x-axis. It's been shifted to the right 5 units, and then up 7 units. I don't have to write all this stuff down to see that. I can just look right here and say that it's been flipped across the x-axis. Remember, I always want to do the flip or the reflection part first. So the parent function, I'm going to start abbreviating this PF for parent function, is flipped across the x-axis, then shifted 5 units opposite direction, so in the positive direction. 5 units to the right, and 7 units up. Okay, there it is. Without even knowing what the parent function looked like, I was able to look at this and describe the transformation. All right? Let me give you guys one to try. All right, I want you guys to describe the transformation that's taking place right here. So we always want to start with flipping the graph, or reflecting, or stretching, or shrinking. We always want to start with that stuff first. I want to take the parent function, stretch it, shrink it, flip it, and then shift left, right, up, or down. So when I look at this, we are stretching this to twice its normal amount. So the parent function is stretched to twice the normal amount If this was something like 1.7, we don't have a word for 1.7, so I'd probably just say the parent function is stretched to 1.7 times the normal amount, right? Then shifted 4 units to the right, and 3 units down. I want to make one quick comment because our book does this. What if this would have been 2 times f of 2x plus 4 minus 3? Okay. What if, same question, but what if I stick a 2 out in front? Well, you know, sometimes we'll look at that and go, oh, well, 2 times 2, that's 4, so we're going to stretch it to 4 times as much. But what if my parent function is a square root function? Then I got to do 2 times the square root of 2 and see what that's equal to. Or what if it's a parabola? Then I'll do 2 times 2 squared. That's 8 times as much. Or what if it's a cubic? 2 times 2 cubed. 2 cubed is 8, times 2 would be 16 times as much. So I don't like it when our book does this, when they put a b value right here, because it really depends on the parent function. It's not just a set answer for all functions. It depends on what the function is. And so I will try to avoid that. Our book doesn't, so you might see a problem or two kind of creep up, but just be aware that's a hard question to answer. You can't answer it until you know what the parent function is. Then you could answer it. All right? So just be aware of that. All right, so we will see some questions like this where they're asking us to describe the transformation, and that's the process right there. All right, so I think we've got enough information for our homework assignment. 3 different things you're going to see. One is you're going to see some graphs where they want you to write the equation that you see. So kind of like what we've done for our entry task. Write an equation that describes that graph. They're also going to want us to describe the transformations, which is what we've done here. They're also going to give us some words and ask us to go back to the equation. All right, remember that thing I told you guys? If you can do things forward and backwards, you probably got it down pretty well. Okay, so we have to think a little bit about that. When we get the words, how do you get back to the equation? So here's our assignment. Number 7, it's Wednesday's work. We're on page 79 to 81. For number 6, we're going to do only parts A through D. Let me just show you real quick what that looks like. All right, so on number 6, we're only going to do parts A through D. What they want us to do is they want us to use this right here as our function. Okay, fine. They just made up a picture. SAT test loves to do this because it makes us think a little harder. It's not a parabola, it's not a square root, it's not a cubic, it's not anything that we know, it's just a picture. So let's look at part E. So they want us to draw what this picture would look like if we were doing f of x minus 3. Well, that minus 3 just means move this picture down 3 units. It's where the D value is. Okay? So I would just reproduce this picture, but 3 units lower than it is right now. If I was doing f, okay, that negative sign means flip this across the x-axis. So these 2 points flip down, these 2 flip up. It now looks like this. Let's see, it goes up, over, and then down. And then shift it down 1 more unit. Okay? Flip it across the x-axis, then shift it down 1 more unit. This is the one that I was telling you, we can't really decide what to do here because we don't know what f of x is. We don't know what the function is. I don't know how to treat it. So I don't even want to assign that one. Okay? But if I had something like this out here, it means just make it twice as much as normal. Here's what's normal. Make all your y values twice as much. So what it really does is it stretches the graph this way to twice its normal amount. Right? So all we're doing is we're just reproducing this picture, but moving it to another part of the coordinate system based on what these say. All right? I also want to just kind of read through these directions because a lot of times students get stuck on this, and I just want to make sure we understand. So it says that g is related to one of the parent functions. These are all g of x here. Identify the parent function. So if I'm doing number 26, the parent function's a parabola. It's f of x equals x squared. Okay, that's what part A is asking for. For this one, it's f of x equals x cubed. What's the parent function? For this one, it's f of x equals the square root of x. Or f of x equals the greatest integer function of x. It's just the x variable with whatever that function is. Part B, describe the sequence of transformations. Okay, so right here with this cubic, I just shifted it to the left 3 units and then down 10. There it is. I've described it. For 26 here, I flip this across the x-axis. I then shift it 10 units to the left and 5 units up. I've described the transformation. Here, I doubled, this is where the 8 number goes, so I stretched to twice as much as what's normal, and then I shifted opposite of that, so to the right, 7 units. All right? So just by looking at this, we're describing the transformation. Then sketch the graph of g. That's what we've spent the last few days doing, learning how to graph these. So draw a picture of the graph. And then use function notation to write g in terms of f. So I want to do one of these. All right? Let's do number 26 here. So this is number 26, and it said g of x equals a negative x. Describe the transformations. Well, if f of x equals x squared, so there's my parent function, then g of x equals f of x plus 10, because what I'm going to do is I'm going to take that x plus 10 and plug it into my function f. I want to flip it across the x-axis, and then I want to shift the whole thing up 5 units. So what they're saying is write g in terms of the function f. F is always the parent function. What am I doing to that to produce this right here? Okay? That's it. That's all they want you to do. Nothing else. But I just want us to understand this. We're establishing the parent function. That's always f of x. And this function g looks the same as this, we're just plugging x plus 10 into this function, which means it goes here. We're then going to take the opposite of it. That's why this negative sign's here. We're then going to add 5. Okay, let me do another one. Let's just look at 34. Okay, absolute value function. Absolute value of a negative x plus 3 plus 9. All right, so there's 34. G of x equals the absolute value of a negative x plus 3 plus 9. So what's my parent function? F of x is just the absolute value of x. And now I need to write g in terms of f. So this function, g of x, is going to equal f of, now the moment I put down f, I'm saying it's an absolute value function. Negative x plus 3, and then plus 9. That's it. I've now written g in terms of the function f, whatever that parent function is. If I just said g of x equals this, we wouldn't know if it's a parabola or a square root or an absolute value or a step function, but we're defining it right here, so now we know, and we're defining it based on what we see here. Okay? All right, and then the last thing they're going to ask us to do in our assignment is they're going to give us the words and ask us to go back and write the equation. Okay, so I didn't do any examples like this. I'm going to make you guys think a little bit. That's a good thing. Force ourselves to think and see how we do with that. All right, that's all I have for you guys for today. There's that assignment again. And I will see you on either Thursday or Friday. All right, you guys, take care. Be safe.